Hi, I'm A.L. Noy, and this is a video about how to convert vectors on your TI-Nspire calculator between polar and rectangular form, and how to add them up when you do that. All right, so here we have the TI-Nspire home screen. What you want to do is you want to press New Document, menu, and what we're going to make is a function which you make inside the programming language of the TI-Nspire, which is called TI-Basic. What you want to do is add a program editor, press New, and we're going to make the first one we're going to make is a two rectangular form, and it's going to be a function. So then you want to press OK, and we're going to define this toRect function, right? And it's going to take in the magnitude of the vector, which we're just going to shorten to mag, and the direction of the vector, which is going to be the angle theta. Now we want a way to get back the information from this function to the main calculator with all the numbers. So the way you do that is with this keyword called return. Now, instead of having to type it all out, what you can do is you can just press menu, transfer, and then return. So we want to return a vector. And in the TI-Nspire line of calculators, the vectors are represented by column vectors, which means that we have the x-coordinate at the top and the y-coordinate at the bottom, surrounded by these square brackets. So for the x direction, what we want is the magnitude of the vector times cosine of the angle of the vector. And for the y direction, we want magnitude times the sine of the angle. Now we want to test if this function really works. So in order to do that, what you want to do is click Control and then R, which will run the function in a separate calculator document. And it already puts you the function, so all you need is to provide the magnitude and the angle of whatever vector you're working with. So here are some examples to just show that this function really works. Notice that we can now just add up these vectors because they're using the format that the Nspire already recognizes. All right, so say now that we have this added up vector, we want to turn it back into its polar form. In order to do that, we're going to need to create a whole new function. So let's create a new program editor window. We're going to name it toPolar, and then this function is going to have two inputs. It's going to have the x and y coordinates of our vector, and it's going to return the magnitude and direction of the angle in its polar form. So in this function, I want to return a list rather than a column vector because I want to make sure that the person understands who's reading this that this isn't an x and y vector. This is just its magnitude and direction. So for the magnitude of the vector, we're going to use the Pythagorean theorem. So it's just going to be the square root of x squared plus y squared. And that's the easy part, but the tricky part comes with the angle. Now, you might be tempted to say that the angle is just the inverse tangent of y over x, but this isn't 100% true because that only applies to angles in the first and fourth quadrants. That's where inverse tangent has an actually defined output. So for the other two quadrants, we're going to need a brand new function, which we're going to call atan2, which is like the conventional name of this function in programming. Now, atan2, it's going to have, again, two inputs, y and the x. They're in this order because usually you do like y divided by x, so it looks the same. In order to determine which quadrant we're in, we're going to need to use something in programming that's called branching. You are probably familiar with branching if you've ever seen a fork in the road. It's basically how a computer makes a decision. Should I go right or should I go left? In a computer, it needs to somehow determine if this condition is true, then I'm going to do this. If it's not true, I'm going to do this. In TI-Basic, this is with the if, then, else, and then end if construction. what happens is whatever comes after if is evaluated. For example, here we want to evaluate if x is greater than 0. That means we're in either the first or fourth quadrant, which means we just want to return whatever inverse tangent gives us because that is the correct number. But if it's not, then we need to have some way else to return something based on other conditions. So what we are going to do is we're going to use the else if construction. So basically, after the if statement is evaluated, every single other else if statements are evaluated. And if one of them is true, then you just run whatever's in there. And if none of them are true, then you go to whatever's in else. So let's run through some of our other conditions. For example, if x is less than 0 and y is greater than or equal to 0, then we're in the second quadrant, which means we want to take whatever tangent inverse gives us, and we want to add 180 degrees just so that it lines up with the right quadrant. Similarly, if x is less than 0 and y is also less than 0, then we're in the third quadrant, which means we want to subtract 180 degrees. Now we want to deal with edge cases, which are basically just examples that don't happen that often. For example, notice how we go with if x is greater than 0 and if x is less than 0. So now we need to test if x is equal to 0. It might not happen often, but we want to make sure that if it does happen, the program is prepared for it. So if x is equal to 0 and y is greater than 0, then what we want to return is just 90 degrees because that just means that it's facing straight up. Similarly, if x is equal to 0 and y is less than 0, then it's just negative 90 degrees because it's just facing directly down. Now, if the only other case that isn't completed by the previous cases is when x is equal to 0 and y is also equal to 0. That will just end in the else statement, and since 0 divided by 0 is undefined, we can just return undef, which just means undefined for the TI-Nspire. Okay, so again, you want to press Control R to test the function, and here are just some examples of some numbers you might want to plug in. Notice how all the edge cases have also been tested and they all work. So now we can go back to the original two-polar function and finally put in a tan 2 y comma x as our angle for the polar version of this vector. Now you can input any x and y and it should give you the correct magnitude and direction with the right angle in the right quadrant. So here, let's test it out. So this worked really well with simple angles, but imagine if we had more complicated magnitudes and angles for our initial vectors that we wanted to add. Now it's really easy to just add them up and get the x and y coordinate, but if we want to turn this back to polar form, we have to type out both of these numbers in the two-polar function, and this is very tedious because these decimals are like very long, and you might mess up, and so you might not want to deal with that, and you might want to just input the vector directly into the function. So to do this, we're going to make a new program. We're going to call this two-polar v, and this program is just going to accept the vector by itself and give out the answer, so you won't have to like manually type it out. So the argument is just going to be the vector, and what we're going to do is we're just going to use the two-polar function that we used earlier, and we're going to return it. But in order to use a two-polar function, we need the x and y coordinates of the vector. So in order to get the x and y coordinates of a column vector in the TI-Nspire, what you do is you press these square brackets on the bottom left using control and then left bracket, and you do 1, 1 for the first column, first row, and then you can, so that will give you the x coordinate, and you can use vector brackets 2, 1 for the second row, first column, which gives you the y coordinate of this vector. So now you should be able to just input a vector directly into this two-polar v function, and it should still give you the magnitude and direction. And you can see here it works beautifully well. So we can finally just use the two-polar v function here, and just put in the answer because that was in the column vector form, and get our final answer of 1.91 magnitude and 77.5 degrees, which makes sense because it's between 30 degrees and 125 degrees, which were our original vector. So now all you need to do is just save this document in your calculator. You can always just use it for whenever you need to convert between polar and rectangular forms of a vector. And it makes adding vectors, subtracting vectors so much easier because you don't have to do any of the math yourself. You don't have to write out like the cosines and sines and inverse tangents and remember which one to use in which case. The calculator just handles it automatically for you. So thank you for watching the video, and I hope you enjoyed.